Look up at the night sky. See those countless points of light scattered across the darkness. Each one represents a world we dream of touching, a destination we imagine reaching. For generations we have gazed upward with longing, convinced that the cosmos is ours to explore, that given enough time, enough ingenuity, enough determination, we will spread across the stars like seeds on cosmic winds. We have built rockets that pierce the atmosphere. We have walked on the moon. We have sent machines to the edge of our solar system and beyond. Every achievement whispers the same promise. We are destined for the stars. But what if that promise is an illusion? What if, despite all our technological triumphs, despite our dreams of Mars colonies and interstellar voyages, humanity is trapped on Earth not by choice, but by the fundamental laws of physics themselves? What if the universe has built an invisible prison around our world, one constructed not from bars of metal, but from the immutable architecture of space-time, energy, and cosmic distance? Tonight, we will explore a possibility that challenges everything we believe about our future among the stars. We will examine the hidden barriers, the silent constraints, the mathematical realities that may keep humanity forever bound to this pale blue sphere. This is not a story of defeat, but of understanding, of seeing clearly, perhaps for the first time, the true nature of the cosmic cage that surrounds us. From where we stand, space appears accessible. The moon is only 3 days away. Mars, a mere 7 months. The outer planets, years perhaps, but reachable. We see distance and we calculate time, engines and fuel, trajectory and velocity. We imagine that space travel is simply a matter of building better rockets, of waiting for better technology, of persisting until we break free. But space is not merely distance, it is resistance. Every mile outward demands exponentially more energy than the last. Every passenger requires life support that multiplies the weight, which demands more fuel, which increases weight further still, spiraling into a mathematical trap that has no simple escape. And distance is only the beginning. Beyond the engineering challenges lie barriers we speak of less frequently. The silent erosion of human biology in zero gravity, the invisible assault of cosmic radiation, the psychological weight of isolation measured not in weeks, but in years, decades, lifetimes, the staggering economic cost of maintaining even a single human in the void. The impossibility of true self-sufficiency when every resource, every spare part, every breath of air must be manufactured from nothing or shipped across millions of miles at crushing expense. These are not problems waiting for solutions. They may be constraints woven into the fabric of reality itself. The universe is vast beyond comprehension, yet that vastness may not be an invitation. It may be a moat. Between us and the nearest stars lie distances so profound that even light, the fastest thing in existence, takes years to cross them. Human lifetimes become meaningless against such scales. Our fastest spacecraft would require tens of thousands of years to reach even the closest neighbouring star systems. We are not separated from the cosmos by miles, but by gulfs of time that swallow generations whole. Tonight, we will journey through the hidden physics that bind us here. We will examine the rocket equation that makes every journey exponentially harder. We will explore the biological fragility that makes long-duration spaceflight potentially fatal. We will confront the economic impossibility of sustaining life beyond Earth's protective embrace, and we'll ask the most haunting question of all. Is Earth not just our home, but our permanent boundary, the only world humanity will ever truly know? Before we begin this journey together, I invite you to pause for just a moment. Leave a comment below telling us where you're watching from and what time it is in your corner of our shared world. Let us see how far across this single planet our curiosity has already spread before we ask whether we can ever leave it behind. Now, let us descend gently into understanding. Let us examine the invisible walls of our cosmic prison. Let's begin. At first glance, a rocket launch appears as humanity's triumph over gravity, a column of fire ascending toward the heavens. The roar echoes across continents. The flames illuminate the sky. We watch with wonder as a sleek vessel climbs higher, disappearing into the blue, carrying our dreams of exploring distant worlds. Yet behind this spectacle lies a mathematical truth so unforgiving, so absolute, that it may represent the invisible wall preventing humanity from ever truly leaving Earth behind. This is the tyranny of the rocket equation, and it is perhaps the most fundamental barrier to interstellar travel that exists. The rocket equation was formulated by Konstantin Tsiolkovsky in 1897, long before the first rocket ever reached space. Its elegance is deceptive, a simple mathematical relationship that describes how velocity relates to fuel and mass. Yet within this equation lies a cruel, exponential reality. To go faster, you need more fuel. But fuel has mass, and to carry that mass you need even more fuel, which has more mass, which requires more fuel still. The spiral continues, indefinitely, creating a mathematical prison from which no amount of engineering ingenuity can fully escape. Consider what it takes simply to reach Earth's orbit, a mere 250 miles above the surface. When a rocket sits on the launch pad, approximately 90% of its total mass is fuel. The remaining 10% includes the rocket structure itself, engines, guidance systems, and the tiny capsule that might carry humans or cargo. Of that 10%, perhaps only 2-3% is actual payload, the satellite, the spacecraft, the explorers we wish to send into space. Everything else burns, away in minutes, discarded stages falling back to Earth as the rocket fights against gravity's relentless pull. This is not inefficiency. This is physics. The energy required to lift mass out of Earth's gravitational well is immense. Every kilogram demands fuel, and that fuel must be accelerated along with the payload. The rocket equation tells us that the final velocity depends on the exhaust velocity of the rocket and the natural logarithm of the mass ratio, the initial mass divided by the final mass. Because logarithms grow slowly, achieving higher speeds demands exponentially more fuel. To double your speed does not require twice the fuel. It requires many times more, increasing geometrically with each increment of velocity. Reaching Earth's orbit requires achieving approximately 17,500 miles per hour. At this speed, centrifugal force balances gravity, and an object remains in orbit rather than falling back to the surface. But Earth's orbit is merely the beginning. To journey to Mars requires escaping Earth's gravitational influence entirely, demanding even higher velocities, around 25,000 miles per hour. To reach the outer planets, speeds must increase further still, and to travel to another star, the speeds become almost incomprehensible, requiring velocities measured as fractions of the speed of light itself. Chemical rockets, the technology that has powered every human journey into space, operate near their theoretical maximum efficiency. When hydrogen and oxygen combine in a rocket engine, the reaction releases a specific amount of energy determined by the chemical bonds being broken and formed. This energy limit is set by fundamental physics. We cannot make chemical reactions more energetic than chemistry allows. The exhaust velocity of the best chemical rockets, using liquid hydrogen and liquid oxygen, reaches approximately 4,500 meters per second. This is not a limitation of engineering. It is a limitation written into the atomic structure of matter itself. Even if we constructed a perfect rocket, one with no structural weight, no engines, no guidance systems, only fuel and payload, the rocket equation still imposes its exponential burden. To reach a nearby star within a human lifetime would require velocities around 10–20% the speed of light. At such speeds, the mass ratio becomes astronomical. You would need to carry millions of times more fuel than payload, a ratio so extreme that the rocket would be larger than planets, impossible to construct, impossible to launch, and impossible to accelerate. This is where the dreams of interstellar travel collide with mathematical reality. Engineers and visionaries have proposed alternatives to chemical propulsion. Nuclear rockets promise higher exhaust velocities by heating propellant with atomic reactions rather than chemical combustion. In theory, nuclear thermal rockets could achieve exhaust velocities twice that of chemical engines, reducing the fuel requirement significantly. Yet even this improvement only delays the inevitable exponential wall. Nuclear rockets still require propellant mass, and the mass ratio problem remains, merely shifted to higher velocities. Moreover, nuclear propulsion brings catastrophic risks. A launch failure would spread radioactive material across continents. The political, environmental, and safety barriers are not mere obstacles. They may be insurmountable. Some imagine nuclear pulse propulsion, detonating atomic bombs behind a spacecraft to generate thrust. Project Orion, conceived in the 1950s, proposed exactly this, a ship riding a continuous series of nuclear explosions. The concept is theoretically sound, capable of achieving velocities far beyond chemical rockets. But the engineering challenges are staggering. The spacecraft must withstand repeated nuclear blasts. The shock absorbers required would be immense. The radioactive fallout from launching such a vehicle from Earth's surface would be unacceptable. Even if launched from orbit, the political reality of deploying thousands of nuclear weapons into space makes this vision a relic of a more reckless age. Then there is antimatter, the fuel of science fiction, the ultimate energy source. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's equation, E=mc2. No other reaction approaches this efficiency. Yet antimatter does not exist naturally in any usable quantity. It must be created particle by particle in enormous accelerators at staggering energy costs. Current production yields mere nanograms per year, and the energy required to produce antimatter far exceeds the energy it releases. Antimatter is not a solution. It is an energy deficit disguised as a miracle fuel. Even if we could produce it in quantity, storing antimatter without it touching ordinary matter and annihilating instantly presents engineering challenges that border on fantasy. The fuel paradox tightens its grip the farther we wish to go. Imagine designing a spacecraft to reach Proxima Centauri, the nearest star system, 4.24 light-years away. If we wish to arrive within a human lifetime, say 40 years, the spacecraft must travel at roughly 10% the speed of light, about 67 million miles per hour. At such velocities, even tiny particles of interstellar dust become deadly projectiles. But before addressing that hazard, we must first confront the fuel requirements. Using the rocket equation, and assuming an optimistic exhaust velocity, the mass ratio required becomes incomprehensible. For every kilogram of spacecraft and payload, thousands or even millions of kilograms of fuel would be needed. If we wished to send a modest 10-ton probe to Proxima Centauri, the initial fueled mass might exceed the mass of entire mountains, perhaps even the mass of asteroids. The fuel alone would dwarf any structure humanity has ever built. And this assumes perfect efficiency, no structural mass, no engines, no shielding, just fuel and probe. The numbers become absurd, revealing the equation's true tyranny. This is why SpaceX, Blue Origin, and other commercial space ventures, for all their achievements, have only solved the problem of reaching Earth's orbit. Reusable rockets reduce the cost of spaceflight, but they do not alter the physics. They do not change the exponential fuel requirements. Reaching orbit is vastly different from reaching the stars. The energy to place a kilogram into low Earth orbit is roughly 30 megajoules. The energy to accelerate that same kilogram to 10% light speed is approximately 450 trillion joules, over 10 million times more energy. This is not a gap that innovation can bridge with better engineering. It is a chasm carved by the laws of physics themselves. Even optimistic proposals for interstellar travel, such as laser-pushed light sails, abandon the rocket equation entirely by leaving the fuel behind. Instead of carrying propellant, these concepts propose beaming energy from external sources, enormous lasers in space, to push ultra-thin reflective sails to relativistic speeds. But these designs are not rockets. They're entirely different technologies that trade one set of insurmountable problems for another. The lasers required would demand power outputs rivaling entire civilizations. These sails must be impossibly light yet strong enough to withstand intense radiation. And once accelerated, there is no fuel to slow down upon arrival. The spacecraft becomes a flyby probe, hurtling past its destination at a fraction of light speed with only seconds to gather data before vanishing into the void forever. The rocket equation is not merely a technical challenge. It is a filter, one that may apply to every technological civilization in the universe. If the laws of physics impose the same exponential fuel requirements on all spacefaring species, then perhaps interstellar travel is not a milestone of advancement, but an impossibility written into the structure of reality. The equation does not care about our ambitions, our creativity, or our determination. It simply calculates the relationship between velocity, mass, and energy, and the numbers it returns are unforgiving. To journey between stars, civilizations must either discover new physics, something beyond our current understanding of propulsion and energy, or they must accept that the distances are simply too great, the energy requirements too immense, and the rocket equation too absolute. We have reached the moon. We have sent probes to the edge of the solar system, but these achievements exist within the realm of the possible, measured in velocities of tens of thousands of miles per hour, not tens of millions. The rocket equation stands as a monument to limits, a reminder that the universe, for all its vastness, may also be profoundly isolating. To escape its grip requires not just better technology, but a fundamentally different approach to motion and energy, one that may not exist. Every rocket launched from Earth carries this equation with it, invisible yet absolute, governing how high it can climb, how fast it can go, and ultimately how far humanity can reach. As we watch the flames of a launch fade into the sky, we're not witnessing the beginning of an interstellar journey. We're witnessing the maximum extent of what the rocket equation allows. Beyond Earth's orbit, beyond our moon, beyond even the outer planets, lies a barrier not of distance, but of mathematics. And mathematics, unlike walls of stone or barriers of politics, cannot be torn down. It can only be acknowledged, calculated, and in the end, perhaps, accepted. The tyranny of the rocket equation is complete. It does not forbid us from dreaming of the stars. It simply ensures that those dreams remain exactly that, dreams glimpsed from a world we may never truly leave behind. Beyond Saturn, beyond the ice giants, beyond the frozen edge of our solar system lies something far more daunting than distance. It is the void itself, vast beyond comprehension, stretching between us and the nearest stars with a magnitude that renders human ambition almost meaningless. This is not merely empty space. This is the unbridgeable ocean that separates our world from any other world we might dare to reach. The universe has imposed upon us a speed limit, absolute and unbreakable. Nothing with mass can travel faster than light. This is not a technological limitation waiting to be overcome by innovation or ingenuity. It is woven into the fabric of reality itself, a law as fundamental as time. And this law creates a prison far more confining than gravity, far more absolute than any barrier we have ever faced. To understand the true scale of interstellar distance, we must first abandon the measurements that make sense within our solar system. Light from the Sun reaches Earth in just over 8 minutes. It touches Mars in roughly 13 minutes, Jupiter in 43, and Saturn in about 80 minutes. Even at the edge of our solar system, where Pluto drifts in perpetual twilight, sunlight arrives in approximately 5 hours. These distances, though vast, remain within the realm of human comprehension. But beyond our solar system, the numbers cease to comfort us. They begin to haunt. The nearest star to our Sun is Proxima Centauri, a dim red dwarf situated 4.24 light-years away. To grasp what this means, imagine that light, travelling at 186,000 miles per second, takes over 4 years to bridge that gap. Light does not rest. It does not slow. It moves at the maximum speed permitted by the laws of physics, and yet it requires more than 4 years to reach our nearest stellar neighbour. For us, travelling at the speeds we can currently achieve, the journey becomes something else entirely, a voyage, measured not in years, but in millennia. Consider Voyager 1, humanity's most distant emissary. Launched in 1977, it has been travelling for over 45 years, moving at approximately 38,000 miles per hour. It has crossed beyond the heliopause, beyond the influence of the Sun's solar wind, and entered interstellar space. Yet even at this tremendous velocity, Voyager 1 will not pass near another star for tens of thousands of years. If it were aimed directly at Proxima Centauri, which it is not, it would take more than 70,000 years to arrive. 70,000 years. Longer than recorded human history, longer than agriculture, written language, or civilization itself. This is the reality of interstellar distance. Even at speeds that dwarf the fastest rockets we have ever built, the nearest star remains impossibly remote. But what if we could travel faster? What if we pushed our spacecraft to a significant fraction of the speed of light, say 10% or even 50%? The mathematics seem encouraging at first. At 10% light speed, Proxima Centauri becomes reachable in roughly 42 years, a single human lifetime. At 50% light speed, the journey contracts to less than 9 years. For a moment, the stars seem almost attainable. But then physics intervenes, not with possibility, but with limitation. Accelerating a spacecraft to even a fraction of light speed requires energy on a scale we cannot currently produce. To accelerate a single kilogram of mass to 10% the speed of light demands energy, equivalent to multiple nuclear bombs. To accelerate an entire spacecraft complete with fuel, life support and crew, the energy requirements become astronomical. literally beyond the total energy output of entire nations. And even if we could somehow generate that energy, sustaining it, directing it, and protecting the spacecraft from the forces involved introduces challenges that border on the fantastical. Then there is the problem of time itself. As a spacecraft approaches the speed of light, Einstein's relativity begins to warp the experience of time for those aboard. This is time dilation, the phenomenon where time passes more slowly for objects moving at relativistic speeds. To an astronaut travelling at 90% the speed of light, the journey to Proxima Centauri might seem to take only 2 years. But on Earth, more than 4.5 years would pass. The faster the spacecraft moves, the greater this disconnect becomes. At 99% light speed, time aboard the ship slows dramatically. A journey that feels like months to the crew might span decades for those left behind. This creates a paradox not of physics, but of humanity. A crew that departs Earth to explore the stars would return, if they returned at all, to find that everyone they knew had aged or died. The world they left would no longer exist. Governments, cultures, languages, entire societies could transform beyond recognition. The travellers would become exiles in time, disconnected from their own history, strangers in their own future. This is not space travel. This is exile. And even this assumes we could reach such speeds at all, which remains purely theoretical. No known propulsion system can accelerate a crewed spacecraft to even 1% the speed of light, let alone the significant fractions required to make interstellar travel remotely feasible. Chemical rockets, the kind that propelled us to the moon, are far too inefficient. Ion drives, nuclear propulsion, even theoretical concepts like antimatter engines all fall short of the energy densities required. The rocket equation, that cruel mathematical truth, ensures that the faster we wish to go, the exponentially more fuel we must carry, and fuel has mass, which requires more fuel to accelerate, creating a spiral of impossibility. But perhaps some argue we do not need to reach light speed. Perhaps we can cheat physics itself with wormholes or warp drives, concepts borrowed from science fiction but rooted tenuously in theoretical mathematics. Wormholes, if they exist, would be tunnels through space-time, shortcuts connecting distant regions of the universe. Warp drives, as envisioned by physicist Miguel Alcubierre, would compress space in front of a spacecraft and expand it behind, allowing the ship to ride a wave of warped space-time faster than light without technically violating relativity. These ideas are mathematically consistent within certain interpretations of Einstein's equations. But mathematics is not reality. Wormholes, if they could exist, would require exotic matter with negative energy density, a substance never observed and possibly forbidden by quantum mechanics. They would also be catastrophically unstable, collapsing the instant anything attempted to pass through them. Warp drives face similar impossibilities. The energy required to create an Alcubierre bubble would exceed the mass energy of entire stars. Even if we could generate such energy, the bubble itself might destroy anything inside it with radiation or shred spacetime in unpredictable ways. These are not technologies waiting to be developed. They are speculative fantasies, mathematical curiosities that allow physicists to explore the boundaries of theory but offer no pathway to practical application. To plan humanity's future around wormholes and warp drives is to plan our survival around magic. The truth is simpler and harsher. The speed of light is not merely a limit, it is a wall. And on the other side of that wall lies nearly every potentially habitable world we have ever detected. Proxima Centauri b, an exoplanet orbiting our nearest star, might possess liquid water. But it is 4 to 24 light-years away. TRAPPIST. 1. A system with 7 Earth-sized planets, 3 possibly habitable, lies 40 light-years distant. Kepler 452b, often called Earth's cousin, is 1,400 light-years away. At our current speeds, reaching these worlds would take tens of thousands to millions of years. Even if we could build a generation ship, a massive vessel designed to support human life for centuries or millennia, the challenges multiply beyond comprehension. Such a ship would need to be entirely self-sufficient, recycling air, water and nutrients with perfect efficiency for thousands of years. It would need to protect its inhabitants from cosmic radiation, micrometeoroids, and the slow degradation of machinery in the vacuum of space. It would need to maintain social cohesion across dozens or hundreds of generations, ensuring that distant descendants who never chose this journey remain committed to completing it. And it would need to function flawlessly. A single catastrophic failure, a breach in the hull, a collapse of the life support system, a plague, a rebellion, and the entire mission ends in silence. Another ghost ship drifting through the void. The psychological toll alone is staggering. Imagine being born, living your entire life, and dying aboard a starship, never touching soil, never breathing unfiltered air, knowing that your children and their children and their children's children will endure the same fate, all for a destination they will never see. This is not exploration. This is imprisonment across generations. And even if such a ship reached its destination, even if it survived the journey intact, the inhabitants would arrive at a world they know almost nothing about. Decades or centuries might have passed since the initial observations. The planet's atmosphere, its climate, its habitability could all differ from projections, and there would be no return, no rescue, no second chance. The cosmos has given us a gift, this pale blue dot, this fragile oasis suspended in endless night. But it has also imposed upon us a boundary, not of malice, but of physics. The speed of light ensures that the universe remains vast, that distances remain unbridgeable, and that the stars, no matter how brightly they shine, remain forever out of reach. Voyager 1 continues its silent journey, carrying with it the golden record, a message from humanity to any intelligence that might one day find it. It is a beautiful gesture, poetic and hopeful, but it is also a marker of our limitation. After 45 years of flight, Voyager has barely begun to scratch the surface of interstellar space. It will drift for millennia before passing anywhere near another star, and when it does, we will not be there to witness it. We will be here, on Earth, where we have always been. Some distances cannot be conquered. Some voids cannot be crossed. The universe, in its infinite expanse, has drawn a line, and on this side of that line lies everything we've ever known. To accept this is not to surrender ambition, it is to recognize reality. The stars are beautiful, distant, and unreachable, and perhaps in their unreachability, they teach us the most profound lesson of all. That home is not a place we leave behind in search of something greater. Home is the place we must learn to cherish, because it may be the only one we will ever have. Our spacecraft drifts through the void, systems humming softly in the darkness. Inside, protected by mere inches of metal and composite material, a human being floats in microgravity. Outside, the universe presses against the hull with forces that have shaped stars and shattered worlds. In this moment, suspended between Earth and the infinite, we confront an uncomfortable truth. Humanity was not designed for this place. Every cell, every bone, every heartbeat was sculpted by 4 billion years of evolution under the constant pull of Earth's gravity, beneath the protective shield of its magnetic field, within the rhythms of its 24-hour day. Space is not merely inhospitable to human life, it is actively hostile to it. And the fragility of our biology may be the most insurmountable barrier to our dreams of becoming a spacefaring civilization. The first assault begins immediately upon leaving Earth's gravity. In microgravity, the human skeleton begins to dissolve. Without the constant stress of supporting body weight against gravity's pull, bones shed calcium at a rate of 1 to 2% per month. Astronauts on the International Space Station lose more bone mass in a few months than a postmenopausal woman loses in a year. This is not merely weakness, it is structural disintegration. The bones become porous, brittle, transforming into something resembling coral more than the dense structures that once carried us across Earth's surface. Hip bones, spine, femurs, the weight-bearing architecture of the body crumbles slowly but relentlessly. Exercise helps slow the process, but cannot stop it. Even with hours of daily resistance training, astronauts return from 6-month missions with bones that may never fully recover. For a journey to Mars lasting 18 months, or a permanent settlement beyond Earth, this degradation becomes catastrophic. The calcium flooding the bloodstream creates another danger: kidney stones, vascular calcification, and internal poisoning by the very substance that once gave us strength. Muscles atrophy alongside bone. Without gravity to resist, the body sees no reason to maintain the vast network of fibers that once allowed us to walk, run, and climb. Leg muscles shrink first, then the back, then the core. The heart itself, that tireless pump that beats 100,000 times each day, begins to weaken. In space, blood does not pool in the legs as it does on Earth. The cardiovascular system adapts by reducing blood volume and allowing the heart to shrink. Upon return to gravity, astronauts struggle to stand, their hearts unable to pump blood efficiently against Earth's pull. Some faint. Some cannot walk for days. This is after months in space. Imagine years. Imagine generations. A child born in microgravity might develop a heart too weak to ever function on a planetary surface, bones too fragile to support their own weight under gravity's embrace. Beyond the confines of Earth's magnetic field, space radiation becomes an invisible executioner. Cosmic rays, high-energy particles accelerated by distant supernovae, slice through spacecraft hulls as though they were paper. They penetrate tissue, shatter DNA, and leave trails of destruction at the molecular level. Unlike radiation on Earth, which can be shielded with lead or concrete, cosmic radiation consists of particles so energetic that conventional shielding is nearly useless. When these particles strike the hydrogen atoms in water or plastic shielding, they create secondary radiation showers, sometimes more dangerous than the original particle. Astronauts on a Mars mission would receive radiation doses equivalent to getting a full-body CT scan every 5 or 6 days. The damage accumulates. Cells lose their ability to repair DNA. Cancer risk skyrockets. Cataracts cloud vision. Cognitive function declines as neurons are damaged one particle strike at a time. Solar particle events, sudden eruptions from the sun, can deliver lethal doses of radiation in hours. On Earth, our magnetic field deflects these storms harmlessly into the aurora borealis. In deep space there is no such protection. A crew caught outside during a solar storm would face acute radiation sickness, vomiting, seizures, death, within days or weeks. Even inside shielded compartments, the exposure could cut years from their lives. This is not theoretical danger. It is measurable, quantifiable, inevitable. Every moment spent beyond Earth's protective magnetosphere is a moment of cellular damage that can never be undone. The mind deteriorates alongside the body. Human psychology evolved in environments rich with sensory input, changing seasons, varied landscapes, the presence of other living things. Space offers none of this. The inside of a spacecraft is monotonous, confined, unchanging. Days blur into weeks, weeks into months. Astronauts report feeling disconnected, experiencing depression, struggling with motivation even on missions lasting only months. The overview effect, that profound sense of awe upon seeing Earth from space, can reverse into a crushing sense of isolation. Earth becomes a distant blue dot, unreachable, impossibly far. Everyone you've ever known, every familiar place, every memory tied to sensory experience exists on that fragile sphere, and you are separated from it by an abyss that cannot be crossed quickly. Sleep becomes disrupted. Without the 24-hour cycle of light and dark, without the subtle environmental cues that regulate human biology, circadian rhythms collapse. The body no longer knows when to sleep, when to wake. Melatonin production falters. Astronauts report chronic fatigue, difficulty concentrating, a fog that never fully lifts. This disruption cascades through every system. Metabolism changes, immune function weakens, healing slows. The body exists in a state of constant low-grade stress, never fully resting, never fully alert. Over years, this could lead to premature aging, cognitive decline, an erosion of the very consciousness that makes us human. The immune system, that magnificent defense network that protects us from pathogens, begins to fail in space. Studies show that T-cell function declines, leaving astronauts vulnerable to infections. Dormant viruses, held in check by the immune system for years, reactivate. Herpes, chickenpox, Epstein-Barr, viruses that lurk in our cells suddenly resurge. Wounds heal more slowly. The risk of infection from even minor injuries increases. In the closed environment of a spacecraft, where air is recycled and surfaces are touched repeatedly, infections can spread rapidly. A common cold becomes dangerous. A bacterial infection could be catastrophic. There are no hospitals in space, no emergency rooms, no access to the vast infrastructure of medical care that we take for granted on Earth. Perhaps most troubling is the question of reproduction. Can humans reproduce in space? Can a fetus develop normally in microgravity? No one knows. Animal studies suggest profound problems. Pregnant rats in space show disrupted development, skeletal abnormalities in offspring, difficulty with balance and coordination after birth. Fluid distribution changes in microgravity. The placenta may not function correctly. Childbirth itself, a process that relies on gravity to help position the infant, becomes mechanically problematic. And if a child could be born in space, what then? Their bones would develop without the stress of gravity, leaving them too weak to ever live on a planetary surface. Their heart and muscles would form in an environment utterly unlike the one their genes expect. They might be beautiful, healthy by the standards of space, but forever exiled from the world that shaped their species. A generation born in space might be the first humans who could never return home. Current shielding technology offers no solution to these problems. The mass required to shield humans from cosmic radiation would be enormous. Tons upon tons of material that must be accelerated, decelerated, and maintained. Water, polyethylene, Even lunar regolith have been proposed, but the engineering challenges are staggering. A spacecraft with sufficient shielding to protect a crew for a multi-year journey would be so massive that our current propulsion systems could barely move it. And shielding does nothing for microgravity. Rotating spacecraft to create artificial gravity are theoretically possible, but have never been built at the scale required for long-duration missions. The technical and financial barriers remain immense. Even if we solve the immediate problems of radiation and microgravity, a deeper challenge awaits. Any colony beyond Earth would require a minimum viable population to maintain genetic diversity and avoid the catastrophic effects of inbreeding. Estimates vary, but most geneticists suggest a population of at least several thousand individuals, perhaps tens of thousands, to ensure long-term survival. Each of these people would need life support, food, water, medical care. They would need to reproduce, raise children, maintain not just technology but culture, language, knowledge. The complexity multiplies exponentially. A space colony is not just an engineering problem. It is an attempt to transplant the entirety of human civilization to an environment actively trying to kill it. We float in the spacecraft, looking through the window at the stars. They seem close, almost reachable. Yet we know now that the distance is not just measured in light years, but in the fundamental incompatibility between human biology and the cosmos. Every system in our bodies, every process from bone growth to immune response, from sleep cycles to DNA repair, was tuned over eons to function within a narrow band of conditions. Earth's gravity, Earth's magnetic field, Earth's atmosphere and day-night cycle. Remove any of these, and the human machine begins to fail. Remove all of them, and we become fragile ghosts, dissolving slowly in the void. The universe is vast, ancient, and indifferent. It does not care whether humanity survives or perishes. Space does not hate us, but neither does it welcome us. It simply exists, governed by laws written long before life began, laws that make no exceptions for consciousness or dreams. Our fragility is not a flaw to be overcome through willpower or technology. It is a fundamental characteristic of what we are, beings of water and carbon, shaped by a specific world, dependent on its protection in ways we're only beginning to understand. As we contemplate the journey ahead, to Mars, to the outer planets, to the stars themselves, we must reckon with this truth. The greatest barrier to human expansion into space may not be engineering or economics, but biology itself. We are Earth's children, and perhaps Earth's children we must remain. We imagine gleaming colonies on Mars, orbital habitats spinning gracefully above Earth, self-sufficient worlds where humanity thrives among the stars. But beneath these visions lies a question we rarely ask. Can any human settlement truly sustain itself beyond Earth? The answer may be written not in the stars but in the fundamental laws of thermodynamics and the intricate web of dependencies that make life possible. A self-sustaining space colony is not merely a technical challenge. It is a confrontation with entropy itself, a battle against the universe's tendency toward disorder. On Earth, we exist within a vast interconnected system that has evolved over billions of years. Every breath we take depends on countless processes, from photosynthesis in distant oceans to the nitrogen cycle maintained by invisible microbes in soil. We do not sustain ourselves. The planet sustains us. In space, we must recreate this entire planetary machinery within the confines of artificial walls, and the task may be impossible. The concept of a closed-loop life support system sounds elegant in theory. recycle the air, purify the water, grow food in controlled environments, transform waste back into resources, create a perfect cycle where nothing is lost and everything renews. But humanity has never achieved true sustainability, even on Earth. Our cities, our nations, our entire civilization operates as an open system, constantly drawing resources from the planet and releasing waste into the environment. We mine metals, burn fossil fuels, consume forests, and rely on Earth's vast capacity to absorb our impact. Remove that planetary buffer and the equation collapses. Consider the International Space Station, our most advanced outpost beyond Earth. It orbits just 250 miles above the surface, close enough to see the continents below. Yet despite decades of engineering refinement, the ISS cannot sustain itself. It requires regular resupply missions carrying water, food, spare parts, and equipment. Its life support systems recycle some water and oxygen, but losses are inevitable. Seals leak, filters degrade, systems fail. Without constant deliveries from Earth, the station would become uninhabitable within months. This is not a failure of technology. It is the nature of closed systems. They leak, they decay, they require constant input of energy and materials to maintain order against the relentless pull of entropy. Now imagine scaling this challenge to a colony of thousands, or even millions. The material and energy requirements become staggering. A space habitat is not just walls and air. It requires power generation, water storage, food production facilities, manufacturing capabilities, medical systems, communication networks, radiation shielding, and backup systems for every critical function. Each component has a finite lifespan. Solar panels degrade in the harsh radiation of space, water pipes corrode, air filters clog, electronic systems fail. On Earth, we replace these components using a global industrial base that spans continents. Mining operations extract raw materials, refineries process metals, factories manufacture semiconductors, plastics, and precision parts. Supply chains connect thousands of specialized facilities, each dependent on countless others. In space, this infrastructure does not exist. The manufacturing problem reveals the deepest layer of the trap. Building complex technology requires not just resources but an entire pyramid of industrial capability. To manufacture a computer chip, you need purified silicon. To purify silicon, you need chemical refineries. To build refineries, you need steel and sophisticated machinery. To produce steel, you need iron ore, coal, and blast furnaces. To mine ore, you need excavation equipment, which requires its own manufacturing base. The chain extends backward through layers of dependency until it reaches the raw planetary resources only Earth can provide. A space colony cannot simply mine asteroids and begin manufacturing. It must recreate the entire industrial pyramid, a process that took humanity centuries to develop and requires resources measured in continents, not habitats. Food production presents its own insurmountable obstacles. Agriculture on Earth is not merely planting seeds and adding water. It is a delicate dance with billions of microorganisms that live in soil, decompose organic matter, fix nitrogen from the atmosphere, and create the fertile medium in which plants thrive. This soil ecosystem took hundreds of millions of years to evolve. In space, we must grow food in sterile environments, hydroponics or aeroponic systems that replace soil with nutrient solutions. These systems can produce lettuce and herbs for astronauts on short missions, but scaling them to feed an entire colony reveals fundamental limitations. Plants require not just water and light, but precise ratios of nitrogen, phosphorus, potassium, and trace minerals. These nutrients must be constantly replenished. On Earth, they cycle naturally through decomposition and geological processes. In a closed system, every harvest removes nutrients that must be replaced. Waste must be processed back into usable fertilizer with perfect efficiency, or the system slowly starves itself. But perfect efficiency violates thermodynamics. Every process loses energy. Every transformation generates waste heat. Every cycle introduces small losses that accumulate over time. Consider calories. An adult human requires roughly 2,000 calories per day. A colony of 10,000 people needs 20 million calories daily, over 7 billion per year. Producing this through artificial agriculture demands enormous energy inputs for lighting, climate control, and water circulation. Even with advanced LED systems and optimized growing conditions, the energy cost per calorie produced far exceeds traditional Earth-based agriculture, which benefits from free sunlight, natural rainfall, and eons of soil development. In space, energy itself becomes the limiting resource. Solar panels degrade. Nuclear reactors require fuel and maintenance. Fusion remains decades away, if it proves possible at all. Without abundant, reliable power, food production cannot scale. The entropy problem looms over every aspect of colony design. The second law of thermodynamics tells us that in any closed system, disorder inevitably increases. Maintaining order, whether in the form of organized molecules, functioning machines, or living organisms, requires constant energy input. A space colony is fighting a losing battle against the universe itself. Every day, materials corrode, systems break down, seals crack, and complexity gives way to chaos. On Earth, this decay is absorbed by the planet's vastness. A broken machine can be replaced with raw materials drawn from the crust. Failed crops are offset by abundant harvests elsewhere. In the confined volume of a space habitat, there is no elsewhere. Every failure must be repaired with limited resources, and every repair draws down finite reserves. Perhaps the most sobering evidence comes from Biosphere 2, an ambitious experiment conducted in the Arizona desert during the 1990s. 8 people were sealed inside a 3-acre glass structure designed to be a self-sustaining ecosystem, complete with rainforest, ocean, agricultural zones, and living quarters. The goal was to prove that humans could create closed ecological systems, a proof of concept for space colonization. The experiment failed. Within months, oxygen levels began dropping as soil microbes consumed more oxygen than plants could produce. Carbon dioxide spiked, forcing operators to pump in air from outside. Crops failed due to pest infestations and pollination problems. The fish in the ocean zone died. Conflicts arose among the crew as psychological stress mounted. After 2 years, the project was abandoned, its primary lesson learned. Closed ecosystems are far more complex than we imagined, and replicating Earth's life support systems may be fundamentally impossible at small scales. Biosphere 2 had advantages no space colony would possess. It existed on Earth, with normal gravity, free sunlight, and relatively easy resupply if needed. It occupied 3 acres, vastly larger than any proposed space habitat. Yet it could not sustain 8 people for 2 years. Scaling this failure to space magnifies every problem. Lower gravity affects plant growth and human health. Radiation requires massive shielding. Resupply from Earth takes months or years. The margin for error approaches zero. Even if we imagine breakthroughs in recycling technology, perfect nutrient recovery and fusion power, one challenge remains: the supply chain. Modern technology depends on rare earth elements, complex alloys, and precision manufacturing that requires global infrastructure. A smartphone contains dozens of elements from across the periodic table, assembled in factories supplied by mines, refineries, and chemical plants scattered across continents. A single advanced computer chip requires hundreds of manufacturing steps, each demanding ultra-pure materials and billion-dollar fabrication facilities. A space colony cannot import these supply chains. It must either recreate them entirely, an impossible task for a small population, or remain forever dependent on shipments from Earth. Calculate the logistics of that dependence, and the colony reveals itself as not self-sustaining, but a fragile extension of Earth's industrial base, perpetually one delayed shipment away from collapse. Every spare part, every replacement filter, every new solar panel must be manufactured on Earth, launched through expensive rockets, and transported across millions of miles. The cost is not merely financial, it is existential. A colony that cannot sustain itself is not a new home. It is a remote outpost, valuable only as long as Earth chooses to support it. Should economic conditions change, political priorities shift, or supply missions fail, the colony becomes a tomb sealed in vacuum. The dream of self-sustaining space colonies rests on an assumption that may be false, that life's complexity can be compressed into artificial systems, that Earth's 4 billion years of evolution can be replicated in steel and glass, that humanity can thrive disconnected from the planetary web that created us. But every attempt reveals the same truth. We are not independent beings. We are expressions of Earth itself, woven into ecosystems too intricate to fully map, dependent on processes too vast to recreate. To sustain life in space is not merely an engineering problem. It is an attempt to reverse entropy, to build islands of order in the ocean of cosmic disorder. And while we can maintain such islands temporarily, with constant energy and material inputs, the question remains, can they ever stand alone? The evidence suggests they cannot. Every closed system eventually fails. Every artificial ecosystem requires outside intervention. Every space colony, no matter how advanced, remains tethered to the one world in the universe confirmed to support human life. As we contemplate colonies among the stars, we must confront the resource trap, not as a temporary obstacle to be overcome with better technology, but as a fundamental constraint imposed by physics itself. The universe does not accommodate our dreams of independence. It demands constant energy, constant resources, constant connection to the wellspring of life. And that wellspring, for now and perhaps forever, is Earth. Beyond the physics and biology, beyond radiation and distance, there exists another barrier to space colonization, one perhaps more insurmountable than all others. It is not measured in light years or radiation doses, but in currencies, investments, and the cold mathematics of economic return. Money, that most human of inventions, may be the final wall that keeps us bound to Earth. For even if we could overcome every technical challenge, even if we solve the puzzle of interstellar travel, the question remains, who would pay for it? And more importantly, why? To understand the economic impossibility of space colonization, we must first confront the numbers. The International Space Station, humanity's most ambitious orbital structure, cost approximately $150 billion to build and maintain over 2 decades. It weighs roughly 420 tons and houses no more than 7 people at a time. It is not self-sustaining. Every few months, supply missions must launch from Earth, carrying food, water, equipment, and replacement parts. Each launch costs tens of millions of dollars. The ISS does not mine resources, does not grow its own food in meaningful quantities, and produces nothing that could be sold to offset its costs. It is, economically speaking, a research laboratory suspended in the void, entirely dependent on continuous financial support from multiple nations. Now imagine scaling the infrastructure to a colony, not a research station, but a permanent settlement capable of housing thousands. The costs do not increase linearly, they multiply exponentially. A Mars colony capable of sustaining 1,000 people would require not just habitats, but farms, factories, energy systems, waste recycling infrastructure, medical facilities, and the machinery to extract and process resources from the Martian soil. Every component would need to be either transported from Earth or manufactured locally using equipment also transported from Earth. The initial investment would not be billions, but trillions of dollars. And unlike terrestrial projects, there would be no economic return. No product mined on Mars could be sold on Earth at a profit, for the cost of shipping it back would far exceed its value. This brings us to one of the most persistent myths of space economics: asteroid mining. The vision is seductive. Asteroids contain vast quantities of precious metals, platinum, gold, rare earth elements. Some estimates suggest a single metallic asteroid could be worth trillions. But these calculations are fundamentally misleading. They assume Earth-based market prices for materials that, if brought to Earth in large quantities, would immediately crash those markets. Scarcity creates value, eliminates scarcity, and the value vanishes. More critically, the cost of reaching, mining, processing, and returning these materials to Earth would dwarf any conceivable profit. Every kilogram launched into space costs thousands of dollars. Every kilogram of refined metal returned would need to justify not just its extraction cost, but the cost of the entire infrastructure required to extract it. The cost per kilogram to orbit is the silent economic assassin of space colonization dreams. Current launch costs hover around $2,000 to $3,000 per kilogram, even with advances from reusable rocket technology. To establish a functioning Mars colony, we would need to transport millions of kilograms of equipment, supplies, and construction materials. Even if launch costs dropped by an order of magnitude to $200 per kilogram, the price of delivering just 10,000 tons of material, a modest estimate for initial colony infrastructure, would exceed $4 billion. That figure covers only transport, not the manufacturing of equipment, not the decades of research and development, not the life support systems, not the habitats, not the backup systems, not the inevitable failures and replacements. And this assumes a colony on Mars, our nearest viable planetary target. The economics of colonizing worlds beyond the asteroid belt become not just unfeasible, but absurd. The energy costs alone, measured in fuel and time, transform the endeavour into a civilizational project spanning centuries. No government has ever maintained funding for a centuries-long project with no tangible return. No corporation has shareholders patient enough to wait generations for profit. No economic system yet devised by humanity can justify the expenditure of trillions with no expectation of return. We might compare space colonization to historical terrestrial colonization efforts, but the comparison immediately reveals why space is categorically different. European colonization of the Americas was driven by immediate economic incentives: gold, silver, timber, agricultural land, furs, and eventually entire continental economies. Ships could make the journey in weeks or months, not years. Colonists could breathe the air, drink the water, grow crops in the soil. The colonies became self-sustaining within years and profitable within decades. Even then, many colonial ventures failed, bankrupting the investors and nations that funded them. Space offers none of these advantages. There is no air, no water, no arable land. There are no indigenous populations to trade with, no existing resources that can be immediately exploited. Every calorie of food, every breath of air, every drop of water must be manufactured or transported at staggering cost. Consider the opportunity cost. The estimated cost of establishing a permanent Mars colony has been calculated by some researchers at 1 trillion or more over several decades. That sum could, if invested on Earth, end extreme poverty globally. It could fund the transition to renewable energy across entire continents. It could build infrastructure, cure diseases, educate billions. The question is not merely whether we can afford space colonization, but whether we can justify it when the same resources could transform life for every human currently alive on Earth. In a world still struggling with hunger, disease, and inequality, the allocation of trillions to establish outposts on lifeless worlds becomes not just economically questionable, but morally complex. No government would fund such an endeavour without political will, and political will requires public support. Public support requires tangible benefits. What benefits does a Mars colony offer to citizens struggling with earthly concerns? What return justifies the diversion of national resources? The Apollo program, often cited as proof that humanity can achieve great things in space, cost approximately $280 billion in today's dollars and was sustained for less than a decade. It was driven not by economics, but by Cold War competition, a geopolitical rivalry that justified extraordinary expenditure for symbolic victory. Once that rivalry cooled, so did funding. The moon has remained untouched by human feet for over 50 years. If we could not sustain interest in our nearest celestial neighbour, what hope is there for Mars or Europa, or the moons of Saturn? Corporate involvement offers no solution. Private space companies currently operate on government contracts, subsidies, and the promise of future markets that may never materialize. Launch services, satellite deployment, and space tourism for the ultra-wealthy represent niche markets, not the foundation of interplanetary economies. No corporation has proposed a self-funded Mars colony because no business model exists. There is nothing to sell. No market to exploit, no profit to extract. Shareholders demand returns measured in years, not centuries. Corporate charters do not extend across generations. The patient capital required for space colonization does not exist in any economic system humanity has yet created. Even optimistic scenarios, where technology advances dramatically and costs plummet, cannot escape the fundamental problem. Space colonization does not merely require expensive infrastructure. It requires an entire industrial base capable of sustaining itself millions of miles from Earth. Every tool, every machine, every spare part must be manufactured locally, which means transporting not just equipment but factories, refineries, power plants, and the expertise to operate them. The complexity compounds endlessly. A self-sustaining colony is not a single project, but a complete replication of industrial civilization in an environment that actively resists it. The cost is not calculable in conventional terms. It approaches the total economic output of entire nations sustained over lifetimes. We return again and again to the same inescapable conclusion. Space colonization makes no financial sense because it offers no financial return. It is an expenditure without profit, an investment without dividend. In a species governed by economic realities, this is not a minor obstacle. It is a wall as impenetrable as the vacuum of space itself. Dreams of new worlds, of human destiny among the stars, must confront the prosaic reality of budgets, cost-benefit analyses, and the simple question every funding proposal must answer: why? The silence that follows that question is profound. We have no answer that satisfies economics, no response that justifies the cost, and so we remain, bound not by physics alone, but by the ledgers and spreadsheets that govern human civilization. The universe may be infinite, but our resources are not. The stars may call to us, but we are answered by accountants, and their verdict is clear. The numbers do not work, they never have, and unless the fundamental economics of existence change, they never will. In the cold calculus of finance, space colonization is not a frontier to be conquered, but a fantasy to be admired from a distance. It is a dream we carry in our hearts, but cannot carry in our budgets. And perhaps that is the most human truth of all, that our grandest visions are constrained not by imagination, but by the ruthlessly practical question of cost. The universe is 13.8 billion years old. Our galaxy alone contains between 100 and 400 billion stars. Thousands of exoplanets have been confirmed, with billions more, awaiting discovery. The cosmos is vast beyond comprehension, ancient beyond measure, and filled with worlds that orbit distant suns in an endless cosmic dance. Yet when we turn our instruments to the heavens and listen for signs of life, for transmissions from alien civilizations, for evidence of beings who might have conquered the stars before us, we hear nothing, only silence. This absence, this cosmic quiet, is not just mysterious, it is deeply unsettling. It suggests that something is profoundly wrong with our assumptions about life, intelligence, and the destiny of civilizations among the stars. This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who in 1950 posed a simple but devastating question: where is everybody? If the universe is so old and so vast, if planets are so abundant and life so seemingly possible, then where are the extraterrestrials? Where are their radio signals, their megastructures, their colonized worlds? Even if interstellar travel is difficult, a single advanced civilization expanding at just a fraction of light speed could colonize an entire galaxy in a few million years. A blink of an eye in cosmic terms. Yet we see no evidence of this. No von Neumann probes, no Dyson spheres, no trace of civilizations that should statistically exist. The silence is absolute, and it forces us to confront an uncomfortable possibility. Perhaps we are not just alone. Perhaps we're the latest in a long line of civilizations that will never escape their homeworlds. Enter the Great Filter Hypothesis, one of the most profound and chilling ideas in modern cosmology. Proposed by economist Robin Hanson in 1996, the Great Filter suggests that there exists some stage in the evolutionary timeline, from non-living matter to spacefaring civilization, that is extraordinarily difficult, perhaps impossible to pass. This filter could lie behind us, meaning that the emergence of complex life or intelligence is so rare that we are among the first. Or it could lie ahead, meaning that something prevents advanced civilizations from spreading across the galaxy. Something that we have yet to encounter. If the filter is ahead of us, then the silence of the universe is not a mystery. It is a warning, a sign that every civilization that reaches our level of technology eventually faces an insurmountable barrier, one that we're now approaching ourselves. What could this barrier be? Some have suggested that civilizations destroy themselves through nuclear war, ecological collapse, or runaway artificial intelligence. Others believe that the filter is biological, that intelligence itself is a dead end, a trait that leads to self-destruction. But there is another possibility, one that aligns with everything we've explored about the impossibility of space travel. Perhaps the great filter is simply this: interstellar travel is not just difficult, it is prohibitively, fundamentally, eternally impossible for biological beings. Perhaps the reason we hear no signals from alien civilizations is because none have ever left their home planets. The universe may be teeming with intelligent life, each species trapped on their own world, gazing at the stars with the same longing and futility that we do. The silence is not absence, it is isolation. This idea is reinforced by the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee. Their argument is not that life is impossible elsewhere, but that Earth-like planets capable of sustaining complex multicellular life, may be extraordinarily rare. Earth's stability is not luck. It is the result of an improbable chain of cosmic accidents. Our planet orbits within the narrow habitable zone of a stable, long-lived star. We have a massive moon that stabilizes our axial tilt, preventing catastrophic climate swings. We have Jupiter in the outer solar system, acting as a gravitational shield that deflects comets and asteroids away from Earth. We have plate tectonics that regulate atmospheric carbon dioxide. We have a magnetic field that protects us from solar radiation. Remove any one of these factors, and Earth might have become as barren as Mars or as hostile as Venus. The conditions that allowed life to flourish here may not just be rare. They may be unique in our galaxy, perhaps even in our corner of the universe. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the fraction of those where life actually develops. The equation is elegant in its simplicity, but every variable is shadowed by profound uncertainty. Early optimistic estimates suggested thousands, even millions of civilizations. But as our understanding has deepened, many scientists have revised these numbers downward, perhaps drastically. If we factor in the rarity of stable planetary systems, the difficulty of abiogenesis, the narrow window during which a civilization might be detectable, and the possibility that technological civilizations self-destruct or stagnate, the number of communicative civilizations in the Milky Way may be one. Us, alone. But what if our aloneness is not a tragedy? What if it is a revelation? For centuries, humanity has imagined itself as destined for the stars, as a species meant to expand, explore, and colonize. We have framed Earth as a cradle, a starting point, something to outgrow. But what if we have it backwards? What if Earth is not a prison from which we must escape, but a sanctuary we must protect? What if the very factors that make interstellar travel impossible are also the factors that make Earth irreplaceable? No other world in our reach has breathable air, drinkable water, or ecosystems capable of sustaining human life without massive technological intervention. No other planet offers the beauty of forests, the rhythm of seasons, the diversity of life that has evolved alongside us for billions of years. To leave Earth is not to transcend our origins. It is to abandon the only home we will ever have. The great filter, then, may not be a wall. It may be a mirror. It forces us to ask not just where the aliens are, but what we are. Are we explorers destined to spread across the cosmos, or are we caretakers meant to nurture the fragile world that gave us life? The answer may determine not just our future, but whether we have a future at all. If we continue to pursue expansion at all costs, draining Earth's resources in the name of space exploration, we may cross the filter not by leaving, but by destroying the only world capable of sustaining us. But if we accept our cosmic limitations, if we redirect our ingenuity not toward escape but toward sustainability, we may discover that our destiny is not wide but deep. What does a deep future look like? It is a future measured not in light years, but in millennia, not in the number of planets colonized, but in the health of the one planet we inhabit. It is a future where humanity learns to live within Earth's biophysical limits, where technology is used not to transcend nature, but to harmonize with it. Renewable energy systems that power civilization without depleting resources. Closed-loop agriculture that feeds billions without degrading soil or poisoning water. Cities designed not as concrete sprawls, but as living ecosystems integrated with forests, wetlands, and natural systems. Medicine and biotechnology that extend healthy human lifespan, allowing future generations to experience the richness of existence on a thriving planet. Space exploration, yes, but not as a means of escape. As a way to study, understand, and protect the fragile jewel we call home. Consider the technologies already emerging that could sustain Earth for billions of years. Fusion energy, still in development, could provide virtually limitless clean power by replicating the processes that fuel stars. Vertical farming and lab-grown food could feed a population of 10 billion or more without expanding agricultural land. Carbon capture and geoengineering, though controversial, offer potential pathways to reversing climate change and stabilizing Earth's climate systems. Artificial intelligence and automation could reduce human labor, freeing billions to pursue creativity, art, science, and philosophy, rather than mere survival. These technologies do not require leaving Earth. They require committing to it. The contrast is stark. Compare the cost of establishing a self-sustaining colony on Mars, trillions of dollars over centuries, with constant supply lines and inevitable loss of life, to the cost of making Earth sustainable indefinitely. Compare the challenge of terraforming a dead planet to the challenge of preserving a living one. Compare the dream of a few thousand humans struggling to survive in domes on an alien world to billions thriving in a restored biosphere. The numbers are not even close. The only rational choice, if survival and flourishing are our goals, is to stay. And yet this choice requires something difficult. It requires humility. Humanity has long defined itself through conquest, expansion, and dominance. To accept that we may never leave our solar system, that we may be bound to Earth not by choice but by physics, challenges our deepest narratives about who we are. But perhaps that challenge is the filter itself. Perhaps the civilizations that survive are not the ones that conquer the stars, but the ones that learn to cherish a single world. Perhaps wisdom is not reaching outward, but turning inward. Not escaping limits, but living beautifully within them. The great filter, seen this way, is not a barrier to fear, but a boundary to accept. It is the universe's way of saying that life is rare, precious, and fragile. That Earth is not a stepping stone but a destination. That the measure of a civilization is not how far it spreads, but how long it endures. If we are alone in the galaxy, if no other voices call out across the void, then the responsibility is ours alone. Not to conquer new worlds, but to protect the one we have, not to become gods among the stars, but to become worthy stewards of the only garden we will ever know. The silence of the universe is not empty. It is full of meaning. It tells us that we are here, on this pale blue dot, suspended in a sunbeam, drifting through the vastness of space. And it asks us a question that only we can answer. Will we exhaust ourselves chasing impossible dreams of escape? Or will we awaken to the beauty and responsibility of the world beneath our feet? The filter is not ahead of us. It is here, now. In every choice we make about how we live, how we build, and what we leave behind. And perhaps, in the end, the greatest journey humanity will ever take is not outward into the stars, but inward, toward a deeper understanding of home. We have journeyed through the mathematics of fuel and velocity, through the silent void where time stretches and distance becomes incomprehensible, through the fragility of human bodies never designed for radiation and weightlessness, and through the cold calculations of economics that reveal the truth. The universe is vast, indifferent, and unforgiving. Every barrier we have explored, physics, biology, engineering, economics, they all converge on a single conclusion. We are not meant to leave, not because we lack courage or curiosity, but because the cosmos itself has drawn boundaries we may never cross. Yet, this is not a tragedy. It is an invitation. What if Earth is not a prison, but a sanctuary? What if our planet is not a limitation, but the rarest gift in a universe dominated by silence and sterility? In the endless darkness between stars, where temperatures hover near absolute zero and radiation tears, through space unimpeded, Earth glows with warmth. It breathes, it blooms, it cradles oceans that shimmer beneath clouds, forests that pulse with life, and atmospheres that shield us from the very forces that would destroy us elsewhere. To call Earth a cage is to misunderstand what makes it extraordinary. We have spent decades dreaming of Mars, imagining colonies beneath distant skies. But Mars is a tomb of frozen deserts and toxic dust. We have gazed longingly at the moons of Jupiter and Saturn, wondering if life hides beneath their ice. But those worlds are realms of crushing pressure and eternal night. Compared to the unrelenting hostility of the cosmos, Earth is not ordinary. It is miraculous. A single pale blue dot where water flows freely, where air can be breathed without machines, where the ground does not crack open with cold or radiation poisoning does not await every sunrise. Perhaps the true frontier is not outward, but inward. Not escaping Earth, but understanding it, protecting it, and transforming it into something even more magnificent than it already is. Imagine if the trillions of dollars spent designing rockets to dead worlds were instead invested in healing forests, cleaning oceans, and building cities that work in harmony with nature. Imagine if the ingenuity poured into colonizing Mars was redirected toward making Earth truly sustainable for the centuries to come. The greatest adventure humanity could undertake is not fleeing our planet, but learning to thrive upon it permanently, beautifully, and wisely. This is not surrender. It is wisdom. The universe has revealed its scale to us, and in doing so, it has also revealed the profound rarity of home. Every sunrise over Earth's mountains, every wave crashing upon its shores, every storm that waters its deserts, these are not ordinary events. They are cosmic anomalies, delicate expressions of conditions so specific, so finely balanced, that they may not exist anywhere else within 1,000 light years. We are children of this world. Our bones are made of its calcium, our blood carries its iron, and our breath is synchronized with the rhythm of its forests. To embrace Earth is not to abandon exploration. It is to recognize that our greatest achievements may not be written in the stars, but here, in the soil, in the stewardship of the one world that will hold us, feed us, and shelter us for as long as we exist. If this video has changed the way you see our cosmic home, consider subscribing for more thought-provoking explorations of science and space. Leave a comment below and tell us where in the world you're watching from. Let us know if Earth feels different to you now. The universe is vast, ancient and indifferent. But Earth, our Earth, is warm, alive, and ours. That is not a limitation. That is a miracle. And perhaps the wisest thing humanity will ever do is learn to cherish it,